working, sir. Okay. Good evening, everyone. So, last class we have been discussing basic concepts of chemistry from 11th standard, right? Could you please tell me what are the topics we have discussed in last class? Let's have a quick recap. You just tell me the subtopic alone, that is enough.
Ma'am, it was my new class, ma'am.
Okay, Kana, okay, fine. Understood. How about Rakshan, Sharmila, Senthamil Chelvan? Fine. So, last class, as I've told you already, we have started with some basic concepts of chemistry. This is from your 11th standard. So, in this, we have discussed, we know what is matter, atom, molecule, chemical bond, stability, and have to convert one unit to another unit. And after which we have discussed mole concept, which is very important, and we have discussed few problems also. And after which we have discussed empirical formula, molecular formula, and finally we have done with limiting reagent, right? So yet to discuss numerical from limiting reagent, but we have discussed what is limiting reagent, right, Kana? I think we have done with 70% of the chapter. So today we'll start with the numerical for this limiting reagent, after which we'll discuss solution concentration part. Okay. So first, what is limiting reagent? So last class we have discussed what is limiting reagent, and we have done one problem also. I want you to tell me what is limiting reagent. Actually, in a chemical reaction, for example, I have two reactants, A and B, and these two reactants are involved in a reaction to give a new compound C. Uh, According to this stoichiometry, 1 mole of A is reacting with 1 mole of B to give 1 mole of C, right? In a chemical reaction, if any of the reactant's quantity is less than the actual quantity required, then that reactant is called limiting reagent. Okay. If suppose in a beaker, I'm taking 1 mole of A and 0.5 mole of B. Actually, the proper stoichiometry is 1 mole of A has to react with 1 mole of B to give 1 mole of C. But in an experiment, I'm taking 1 mole of A and just 0.5 mole of B. So what it means, the quantity of B is lesser than the quantity it is actually required. So here the limiting reagent is B. Okay. And this limiting reagent will decide the quantity of the product formed. So according to the stoichiometry, 1 mole of A is reacting with 1 mole of B to give 1 mole of C. But in an experiment, I have 1 mole of A and just 0.5 mole of B. So the limiting reagent is B. So the quantity of product will be decided by this limiting reagent. So here, if 1 mole of B is reacted, then the quantity of the product formed will also be 1 mole. But here the number of moles of B is just 0.5. So what will be the quantity of product formed? What will be the number of moles of C formed here?
0.5.
Yes, it is 0.5. And once the complete reaction was over, the limiting reagent will be completely consumed. Okay, so this is the few points we have to know whenever we are discussing this limiting reagent. And we may expect, definitely we can expect questions from this limiting reagent concept, Kanna. So we'll discuss few problems in it. Yes, here is the question. So here we are provided with some equation. Here methane is reacting with oxygen to give carbon dioxide and water. Basically, this reaction is a combustion reaction where methane is burnt with oxygen to give carbon dioxide and water. Whenever the process is given, we have to write that process into a chemical equation. Whenever the equation is given, please make sure the equation is a balanced one. So here it is the second scenario. We are provided with some equation and we have to make sure the equation is balanced. Could you please tell me whether the reaction equation is balanced or not? Is it balanced, Kanna?
Mhm.
Yes, it is balanced, right? So, from this balanced equation, what we can infer is in terms of number of moles, 1 mole of methane is reacting with 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water, right? So if 1 mole of methane is reacting, then we'll end up with 1 mole of carbon dioxide. If 1 mole of methane is involved in a reaction, then we'll end up with 2 moles of water. So here is the stoichiometry, right? Now let us come to this question. They're asking us to calculate the amount of water in terms of gram. They're asking us to calculate the amount of water produced by the combustion of 16 gram of methane, right? So here the data is 16 gram of methane is involved in the reaction. Then what will be the quantity of water formed? See, basically our inference is based on the number of moles. If the methane involved is 1 mole, then amount of water formed will be 2 moles. If methane involved is 2 moles, then what will be the quantity of water formed? If methane involved is 2 moles, then number of moles of water formed will be how much, Kana?
One.
It is in the 1:2 ratio. If methane, a number of moles of methane involved is 1 mole, then number of moles of water formed will be 2 moles. If number of moles of methane involved is 2 moles, then what will be the quantity of water molecule formed?
4 mole, ma'am.
1.
4 moles, right? So here the data is in terms of gram. Now we have to convert this weight into number of moles because our inferences are in number of moles, right? So 16 gram of methane is how many mole? So we have a formula, right? Number of mole is equal to given mass divided by molar mass. So now, here we have to calculate number of moles. Given mass is 16 gram. And what is the molar mass of methane? What is the molar mass of methane?
16 gram per mole.
Very good, 16 gram per mole. So here it is 1 mole. So if 1 mole of methane is involved in the reaction, then we'll end up with 2 moles of water, right? But here they're asking us to express in terms of gram. So how many gram of water molecule formed? Number of moles formed is 2 moles. So n is equal to 2. So what will be the quantity in terms of weight? It is 36 gram, right? Am I clear? Sendam children's answer was right. Any doubt, Kanna? Fine. Shall we move on to next question? Okay. Here, the second question is, how many moles of methane are required to produce 22 gram of carbon dioxide? So now here the quantity of product was given. Here carbon dioxide carbon dioxide quantity is 22 gram. So if 22 gram means what is the number of moles of carbon dioxide formed? weight of carbon dioxide is 22 gram, and our inferences were in terms of number of moles. So first we have to convert this weight into number of moles. So here 22 gram of carbon dioxide is given. So how many moles of carbon dioxide is that? So what is the
0.5
formula?
mole.
Yes, it is 0.5. So here in given data, carbon dioxide formed as 0.5 mole, which means how many moles of methane required to produce this 0.5 mole of carbon dioxide. What was the original ratio? If methane's number of mole is 1, then carbon dioxide number of mole is also 1. They are in 1:1 ratio. If carbon dioxide formed as 0.5, then how much quantity or how many number of moles of methane involved? What should be the quantity of methane then?
0.5 mole, ma'am.
Very good. It is also 0.5 mole. If they're asking it in terms of gram, then how many gram of methane required to produce 0.5 mole of carbon dioxide?
8 gram, ma'am.
That's it. That's it. So if it is in terms of number of moles, it is 0.5 mole. If it is in terms of gram, then 8 gram of methane required. That's it. So this is how it works. Okay, fine. Now we'll move on to next question. See, 10 gram of hydrogen and 64 gram of oxygen were filled in a steel vessel and exploded. Amount of water produced in this reaction will be dash. See, in this question, they are talking about some process. So we have to write the chemical equation for this process. That will be the first step. So here, what are all the reactants involved? Hydrogen and oxygen. Hydrogen and oxygen reacted together to give water, which is H2O, right? Now, second step is we have to balance the equation. Could you please balance this equation? Kana, please balance this equation, Kana. Tell me the number of moles of each species. So, left side I have 2 hydrogens, right side I have 2 hydrogens, hydrogens were balanced. Left side I have 2 oxygen, right side I have only 1 oxygen, so I have to include 2 here. Now oxygen is balanced, but hydrogen is disturbed. So right side I have 4 hydrogen, left side I have only 2 hydrogen, so 2 moles of hydrogen. So this is the balanced equation, right? Is it balanced now? Is it balanced now?
Yes, ma'am.
Yes. So 2 moles of hydrogen is reacting with 1 mole of oxygen to give 2 moles of water molecule. So the inference is 2 moles of hydrogen is reacting with 1 mole of oxygen to give 2 moles of water. So if 1 mole of oxygen reacts, then it will give 2 moles of water molecule. If 3 moles of oxygen reacts together, then it will give 6 moles of water molecule. So here is the inference. So could you please tell me the data given? What is the data, Kana? 10 gram of hydrogen is reacting with 64 gram of oxygen. And they're asking us to calculate the amount of water formed. Whenever the data is given in terms of weight, then we have to convert that into number of moles. So first step is we have to convert this weight into number of moles. So what is the formula? Number of mole is equal to given mass divided by molar mass. So what is the given mass of hydrogen? It is 10 gram. And what is the molar mass of hydrogen? What is the molar mass of hydrogen? It is hydrogen molecule. So it is 2 gram per mole. And given mass of oxygen is 64 gram. And what is the molar mass of oxygen molecule? Oxygen molecule. Atomic weight of oxygen is 16. And here we have 2 oxygen. So molar mass is 32 gram per mole. So what is the number of moles of hydrogen then?
5 mole, ma'am.
Yes, 5 mole. And what is the number of moles of oxygen?
2 mole.
2 mole, ma'am.
5 moles of hydrogen and 2 moles of oxygen were reacted. Now we have to find the quantity of water formed. Actually, what is our inference? 2 moles of hydrogen will react with 1 mole of oxygen. Actually, the quantity of oxygen required is half the quantity of hydrogen, or the quantity of hydrogen required is 2 times the quantity of oxygen, right? Now let us come to this data. Here, hydrogen's number of mole is 5 mole. And what should be the quantity of oxygen formed? What should be the quantity of oxygen should get involved in the reaction? If it is 2 mole, oxygen has to be 1 mole. Here it is 5 mole. Then oxygen's number of moles has to be half of this 5 mole, which is 2.5. Right, Kana? But what is the given quantity of oxygen? It is just 2 moles. Right? So here, who's the limiting reagent? Here, which is the limiting reagent?
Oxygen.
Oxygen is the limiting reagent. So this oxygen will decide the quantity of water formed. Formed is twice that, right? It is 2 moles. Here, 2 moles of oxygen is involved in the reaction. Then what will be the quantity of water molecule formed?
4 mole.
That's it. That is the
4,
answer.
ma'am.
That's it, Kana. Yes. Fine. Now, I'm going to give you one more problem. I want you guys to solve now. How many moles of lead chloride will be formed from a reaction between 6.5 gram of PbO and 3.2 gram of HCl? Here also we are provided with some process. First step is we have to write the equation. Could you please tell me the equation for this? What are all the reactants here? PbO, and there is lead oxide and HCl. And what is the product formed? Lead chloride. See here, this 2 represents the oxidation state of lead. So this is Pb2 plus and this is Cl minus. So what will be the compound? What will be the formula of the compound formed? It is Pb. See, this is
PbCl.
Pb. It is not just Cl, Kana. See, this is Pb2 plus and this is Cl minus 1. So to find the proper formula, we have to do this crisscross method, right? So we have to multiply this 2 with P, 1 into 1 about. Now we have to balance this equation. Okay. So lead is balanced, but hydrogen is not, chlorine is not balanced, right? And also we have, chlorine is not balanced. So we have to balance the chlorine. So left side I should have 2 HCl, right? And what is the remaining atoms which is not balanced, Kana? Hydrogens were not balanced and oxygen is not balanced also, right? So right side I'll be having 1 water molecule. Is it balanced now? Is it balanced now? Okay. Now please solve this problem and come up with the answer. What is the inference? 1 mole of lead oxide is reacting with 2 moles of HCl to give 1 mole of lead chloride and 1 mole of water, right? And we have to know the data. PbO involved in the reaction is 6.5 gram. So we have to convert the 6.5 gram into number of moles, and the number of, weight of hydrochloric acid is 3.2 gram. Again, we have to convert this given mass into number of moles. And from the number of moles, we have to find the limiting reagent, and that limiting reagent will decide the quantity of lead chloride formed. Is it possible for you guys to solve this problem? Can you do this as activity?
Yes, ma'am.
Yes. So if you can do it on your own, then I'll give this as activity. Now we'll move on to next problem. Or if you cannot, or if you don't have confidence in solving it, please let me know. We'll do it together. What shall we do? Is it possible for you guys to do it? Sendamil Chelvan is okay with it. But how about rest of the students? It is similar to the last problem. Shall we have this as activity then?
Yes, ma'am.
Okay, right. After solving, please share it in the group, okay? I'll check. Fine. Now we'll move on to next new concept in this chapter. So we have discussed very important topic, which is mole concept. We have to know how to convert weight into number of moles and number of moles into number of chemical species. And we have discussed how to calculate empirical formula and molecular formula of the given compound. And we have discussed what is limiting reagent and how to find the limiting reagent, and we have discussed numerical also. Now we're going to discuss the last topic of this chapter, which is solution. In this chapter, we'll be discussing what is solution and a few parameters related to this solution. See, in 12th standard, we have a complete chapter for solution itself. So in 12th standard, we're going to learn in depth, but in 11th standard syllabus, in this very first chapter, they've given the introduction for this solution. Kana. So let us understand few fundamentals related to this solution. That is enough. But in 12th standard, we're going to learn in depth. Fine. If you guys are from state board, in 11th standard, in some basic concepts of chemistry, you have studied redox reaction also. But since I'm following the CBSE pattern, now we will not be discussing this redox reaction. But after 5-6 chapters, we have a complete chapter for redox reaction itself. At that time, I'll be discussing redox reaction. Okay. But according to CBSE, this is the last topic of this chapter. Okay. So solution. So shall we start with solution then? Shall we? But please, before getting into this, I want you guys to be very interactive. It is really boring. It is boring for me, and definitely it will be boring for you also. Okay, I want you guys to interact. Just talk. That is enough. Huh? Fine.
Okay, ma'am.
Right. So now we'll start with solution. See, the terms what I'm going to discuss now is solution, solute, solvent, molarity, molality, normality, and all that. And I know these terms are not new to you, right? Fine. Now, what is solution? What do you know about that? Or tell me the solutions you know. Okay. For example, I have a beaker full of water. Is it a solution? I have a beaker full of water. Is it a solution? No.
Yes, ma'am.
Okay, I have beaker full of water. Water is not a solution. Okay. I have a beaker full of water into which I am adding a salt. It can be any salt and it got dissolved. Is it a solution now?
Yes, ma'am.
Yes.
Okay. Into the same beaker, I'm going to dissolve sugar also. Is it a solution?
Yes, ma'am.
ma'am.
Okay, fine. Now I have a fresh beaker of water into which I'm adding few drops of coconut oil. Is it a solution?
Yes, ma'am.
Okay. I'm going to give you a definition for solution. After giving the definition, you tell me which are all the solutions here. Solution is a homogeneous mixture of two or more components. So it is not a single component. Okay, it is a mixture, and it is not just a mixture, it is a homogeneous mixture. What is mean by homogeneous mixture?
A solution without boundaries.
Okay. Throughout the system, we can see only one physical state. Then that is called homogeneous mixture. For example, I have beaker full of water. It is not a solution because it is just one component system into which I'm adding salt and it got dissolved. Once the salt is dissolved inside water, we cannot differentiate salt from water, right? So throughout the beaker, I can see only one system or only one physical state. So that is called homogeneous mixture. So the system will be uniform. So solution is a homogeneous mixture of two or more components. So I had water. Water is not a solution because it is one component. But into which I've added salt and it got dissolved also, it is a solution. Into which I'm adding sugar. So I have three components, and of course, salt, sugar will get dissolved inside the solution, and throughout the system, it will be uniform. So that is also a solution. And the final example was water with coconut oil. It is a two component system, but oil will not get dissolved inside water. I can differentiate oil from water. So it is a heterogeneous mixture. So this is not a solution. So solution is nothing but it is a homogeneous mixture of two or more components. Am I clear now? Okay, now we will move on to next two terms, which is solute and solvent. In a solution whose components, whose quantity is very much lesser than that is solute, whose quantity is higher than that is solvent. For example, I have beaker full of water. For example, I have 100 ml of water into which I'm adding 1 gram of salt. So here 1 gram of salt is the substance whose quantity is lesser. Then this is solute. And water is your solvent. If it is a three component system, 100 ml of water into which I'm adding 1 gram of salt and 1 gram of sugar, then sugar is also one of the components, right? So I have two solutes here. So salt and water, and I mean salt and sugar were two solutes, and water is the solvent. So solute plus solvent is equal to solution. You getting my point, Kanna? So solvent is the component whose quantity is very large. Solute is the components whose quantity is very less. Fine. So we are done with solution. We are done with solute and solvent. Next, we'll move on to concentration. Concentration is nothing but the quantity of the solute present in the particular quantity of the solvent or quantity of the solute present in the solution. This is called concentration. Okay. Whenever the solution is given, we have to know the concentration of the solution. Concentration is nothing but the quantity of the solute present in the solution, or quantity of the solute we're going to add inside the particular quantity of solvent. Okay, so that is concentration. I have a first beaker into which I have water, which is a solvent, and into which I'm adding solute, which is salt. Let us say it is sodium chloride. I'm going to add 1 gram of sodium chloride here. In second beaker also I have same quantity of water into which I'm going to add same salt, which is NaCl, but the quantity here is 2 gram. Could you please tell me whose concentration is greater among A and B? Which beaker got higher concentration of higher concentrated solution? Is it 1 or 2?
B.
Exactly, because the quantity of solute in second beaker is 2 gram, right? So here this is considered to be the higher concentrated solution, right? Next, the term we're going to understand is solubility. Solubility. For example, I have a beaker full of water, let us say 100 ml, and in which I can add a salt called AB, and maximum quantity I can add is only 7 gram. After this 7 gram, I cannot even dissolve 0.1 gram of the salt. So the maximum quantity of salt that can be dissolved in a particular quantity of solvent, then this is the solubility of the salt. Okay, only 7 gram can be dissolved. See, this is the hypothetical salt and this is the hypothetical solubility. Each salt will have its own solubility. You're getting my point?
Yes, ma'am.
So the maximum quantity of salt that can be dissolved in a particular quantity of solvent is the solubility. For example, I have a fresh beaker of 100 ml water into which I am going to add AB salt of 3 gram. Will it get dissolved? Will it get dissolved? Solubility of AB salt is 7 gram. Now I've just added
Yes,
only 3 grams. It will get dissolved because solubility is 7 grams, right? I've just added only 3 gram. It will get dissolved. Into the same beaker, I'm going to add 2 more grams of salt. Will it get dissolved?
Yes, ma'am.
Definitely it will get dissolved. To this beaker, I'm going to add 1 more gram of salt. Will it get dissolved? Yes,
Yes,
because
ma'am.
I've just
Yes,
added
ma'am.
6 gram. Now I'm going to add 1 more gram. Definitely it will get dissolved. Right. To the same beaker, I'm going to add 0.7 gram. Will it get dissolved, Kana?
No, ma'am.
No.
No.
Right. So if the solution contains the salt whose quantity is lesser than its solubility, then that stage of solution is called unsaturated solution. If the solution contains the solute whose quantity is exactly equal to the solubility of that solute, then that is the saturated solution. If the solution contains the solute whose quantity is greater than its solubility, then that is supersaturated solution. In supersaturated solution, we can see the undissolved salt at the bottom. Okay, fine. That's it. Now we're going to move on to the very important concept where we're going to express the concentration in terms of molality and normality, and we can expect questions from this concepts also. Fine. We know what is concentration, right? What is concentration, Kana?
Quantity of solute.
Quantity of the solute which is present inside the solution, or the quantity of the solute we're going to add inside the solvent, right? That is concentration. See, we have different way of expressing this concentration: molality, normality, mole fraction, mass percentage, volume percentage, ppm. All these parameters are used to express this concentration. But in this chapter, we're going to study only few parameters like polarity, molality, normality, and mole fraction. That's it. Rest of the concentration expressions we'll be studying in 12th standard. Okay, fine. See, I've told few parameters like polarity, molality, and all that, right? All these are helpful for us to express the quantity of the solute present inside the solution. For all these parameters, we have an expression, and that expression will be in fraction. Okay, so in the numerator, we'll be having the quantity of the solute, and denominator will be having the quantity of solvent, or in some cases quantity of the solution. Okay, and quantity can be in terms of weight or volume, or it can be in terms of number of moles also. Similarly, quantity of solvent or solution can be in terms of weight, volume, or in terms of number of moles. So this is the normal expression for concentration. For molarity, normality, the way of expressing this quantity may vary. Right. Now we'll move on to the very first concentration expression, which is molarity. Molarity can be represented with an alphabet capital M. Okay, and here is the formula. In numerator, it is going to be quantity of the solute. Here, the quantity will be expressed in terms of number of moles. Number of moles of solute divided by, here, the quantity going to be in volume. Volume of solution. That's it. And here, volume of the solution has to be expressed in liters. That's it. See, this is the formula, Kana. Here, the quantity of the solute is in terms of number of moles, and quantity of the solution, it is in terms of volume. Right. See, this is the expanded formula. But whenever we are writing the formula or the expression, we'll be representing with an alphabet. Okay, see, for number of moles, what is the alphabet, Kana? For number of moles, how we'll be representing? I want to express it in some alphabet. How we'll be expressing?
Small n now.
Very good, small n. For volume?
Capital V, ma'am.
Very good. For weight?
Small W, ma'am.
W, right. So, for number of moles, it is small n. For volume, it is V. Weight, it is a W. And for molecular weight, generally, we'll be using capital M. Okay. And in the subscript is nothing but this one. Okay. In the subscript, if I have 1, then this is the number of moles of solvent. If the subscript is 2, then that represents that property is for solute. If I didn't write anything, then that property is for solution. Okay, fine. Now we'll try to express this formula. See, this is number of moles of solute. So what is number of moles? Small n. This is number of moles of what? It is solute. So what will be the subscript then? What will be the subscript, Kana? Is it 1 or 2, or I shouldn't write anything? It is number of moles of solute. For solute, what is the subscript? It is 2. N2 divided by volume of the solution. So volume is nothing but capital V. For solution, we shouldn't write anything. That's it. So here it is expressed in terms of liters. Now this is the formula of molarity, and I want you guys to tell me the unit of molarity. What is the unit of molarity? That is the representation, Kana. But the unit is number of. Yes. So the unit of number of mole is mole, and unit of volume is liter. So I'm going to bring this liter to numerator. So the unit is mole per liter. So this is the unit of molarity. And here I have another way of expressing this molarity. That is, I'm going to expand this formula. We know what is number of moles, right? What is number of moles, Kanam? What is the formula of number of moles? Weight by molecular weight. Given mass by molar mass, right? So instead of this N2, that is number of moles of solute, I can write it as weight of solute divided by molecular weight of solute into volume of the solution in liters. I can write like this or I can expand like this also. Fine. Any doubt? So I want you guys to solve this problem. It is very easy. Yes. Could you please solve this problem? They're asking us to calculate the molarity of a solution which is prepared by dissolving 3 moles of solute in 5 of solute dissolved to prepare 30 ml of 5 molar sodium hydroxide solution. 5 molar sodium hydroxide solution. They're asking us to calculate the weight. So we should know what formula to be used here. Do you want any clue or any help? If you're doing it, then I'll give you time. Kana, what happened? Are you guys doing it? Rakshan, Ramprasad?
Trying.
Trying. Okay, fine. I'll give you 1 more minute. Okay. I'll give you the formula to be
Ma'am,
used. Yes, Kana?
6 gram, ma'am.
6 gram. Okay. You're right. Fine. So I'm going to tell you how to solve this problem. See, they are talking about molarity. So the only formula we know is number of moles of solute divided by volume of the solution, or weight of solute divided by molecular weight of solute into volume of the solution in liters. Here they're asking us to calculate the weight of solute. So we cannot use this formula. Instead we can use this, right? Here we are provided with molarity, we are provided with the volume of the solution, and they didn't give the molecular mass, but we can calculate the molecular mass of sodium hydroxide, right? So rest of the data are there, so we can calculate W2. So molarity is equal to weight of the solute divided by molecular weight of the solute into volume of the solution in liters, and molarity is 5 molarity, which is mole per liter, and we want to cross multiply this. So if you cross multiply this, what is the molecular mass of sodium hydroxide? Atomic mass of sodium is 23 gram per mole. For oxygen it is 16 gram per mole, and for hydrogen it is 1 gram per mole. So what is the molar mass of sodium hydroxide, Kanna? You just need to add all these stuffs, right? So it is 40 gram per mole. And volume of the solution is 30 milliliter. I have to express in terms of liter. So 30 milliliter. So I've written the value of milli, which is 10 power minus 3. And we need to simplify this. Per mole and mole will get cancelled. Per liter and liter will get cancelled out. So we can express it in terms of gram. If you multiply this, we'll get it as 6 gram. Any doubt? Any doubt, Kanna? Fine. Shall we move on to next question then?
Yes, ma'am.
Fine. See, the next question is going to be little different. Please listen carefully. Okay. What is the problem here? 25.3 gram of sodium carbonate, whose formula is Na2CO3, was dissolved in enough water to make 250 ml of solution. Okay, so here weight of sodium carbonate is given and volume of the solution is also given. If sodium carbonate dissociates completely, then molar concentration of Na plus and CO3 2 minus ion, which is carbonate ion, are respectively dash. See, this problem is little different. Here they are talking about a solution where sodium carbonate is a solute and water is the solvent. And we are provided with the weight of sodium carbonate and volume of the solution, which means W2 is given and V is also given, and definitely we can find the concentration of the solution, right? We can calculate molarity, but they didn't ask for the concentration of the solution. Instead, they're asking us to calculate the concentration of Na plus and CO3 2 minus ion. See, let us understand how to do that. For example, let us forget this problem now. I'm going to give you a hypothetical scenario. I have AB molecule, Kanna. I'm going to take only one AB molecule and I'm going to dissolve inside a solution, or I'm going to dissolve this in water. If this AB molecule is dissociated completely, it will get dissociated into A and B. The first species will have positive charge and second species will have negative charge. So left side I have only one A and right side also I have only one A. Left side I have only one B, right side also I have only one B. So it is a balanced equation, and As I've told you, first species will have positive charge. How many positive charge I should write? How many moles of B is there? Only one. So it should have only one positive charge. And number of negative charge has to be equal to the number of moles of A atom. It is 1, so it is -1 here. Okay, fine. This is how complete dissociation occurs. For example, I have 100 molecule of AB molecule and all the AB molecules were dissociated. Could you please tell me how many A plus and how many B minus I'll be having inside the solution? All the AB molecules were dissociated. How many A plus and how many B minus will be there? How many A plus and how many A minus will be there? Okay, if it is difficult for you, let us say I have only one molecule of AB and it was dissociated completely. How many A plus and how many B minus will be there? I had only one AB molecule which was dissociated. It was splitted into A plus and B minus. How many A plus and how many B minus inside the solution? It will be only
0.5 plus.
No. A plus will be 1 and B minus also will be 1. Okay, because in one AB molecule, I have one A plus and one B minus, right? So it was dissociated. So inside the solution, I'll be having only one A plus and one B minus. For example, I had two molecules of AB. If I had two molecules of AB, then if it is completely dissociated, I'll be having two A plus and two B minus, right? You're getting my point. Suppose I have 1,000 molecules of AB. How many A plus and how many B minus will be there?
1000 A plus 1000 B minus.
Very good, Kana. This is in terms of molecules, right? If it is in terms of concentration, if it is 0.1 molar AB, then after dissociation, I'll be having 0.1 molar A plus and 0.1 molar B minus. This is how it works. This is in terms of molecules and this is in terms of concentration. Fine. If suppose the compound I'm going to dissolve is AB2, how it will get dissociated? It will get dissociated into A and B. How many A atoms are there in the left side? Only one. So here also it has to be 1. Left side I have 2B. So right side also it has to be 2B. And first species will have positive charge. How many positive charge? How many B atoms were there? 2. So it is 2 positive charge. And B should have negative charge. And how many negative charges I should have? Number of A is 1. So I should have only 1 negative charge. Right. Suppose I have only one AB2 molecule and it was completely dissociated. So from this one AB molecule, I'll have only one A2 plus and then I'll be having 2B minus. You're getting my point? Because in one AB molecule, I have one A and two Bs, right? So after complete dissociation, I'll have one A2 plus inside the solution and two B minus inside the solution, right, Kana? Similarly, if I'm dissolving 10 molecules, then how many A and how many Bs will be there? A2 plus and 20, that is 2 into 10, B2 minus, right, Kana? If it is in terms of concentration, if it is 0.1 molarity, then how many how many A2 plus and how many B minus will be there? It is again, this is similar to the concentration of AB2 and it is 2 times the concentration of AB2, right? You guys got my point?
Yes, ma'am.
Fine. Now our job is we have to apply the same concept for this sodium carbonate. How the sodium carbonate will get dissociated? As I've told you, first species will have positive charge, which is sodium, and second species here is CO3. And how many sodium atoms are there? 2 sodium atoms. How many CO3 is there? Only one. First species will have positive charge. How many positive charge? Only one carbonate, so one positive charge. And carbonate will have negative charge. How many negative charge? I have two sodium, so two negative charges. So if I'm dissolving only one molecule of sodium carbonate, how many Na plus and how many CO3 2 minus I'll be having? If I'm dissolving one molecule of sodium carbonate upon complete dissociation, how many Na plus and how many carbonate ions? Yes, and the children?
2 sodium ions and 1 carbonate ion for
That's
each molecule, ma'am.
So, 2 sodium ion and 1 carbonate ion. If it is 10 molecule, then it is 20 Na plus and 10 carbonate ions, right? If it is 0.1 molarity, then 2 into 0.1 molarity of sodium and it is 0.1 molarity of carbonate. So our takeaway point is concentration of Na plus will be the twice the concentration of sodium carbonate, and the concentration of carbonate ion is same as the concentration of sodium carbonate. And also the relationship between the concentration of Na plus and CO3 2 minus is 2:1. Right, Kana? See, these are all the inferences. We can approach this formula in two different ways. One is the logic is here they're asking for the concentration of Na plus and carbonate ion inside the solution. According to the inference, what we know, the concentration of Na plus will be twice the quantity of the concentration of the carbonate ion. Here in this option, see the question is respectively, which means the first is Na plus and second one is CO3 2 minus, and we know the concentration of Na plus is twice the quantity of carbonate ion, which means we can screen the options. First option will be ruled out. Why? Definitely first option will not be our answer. Why, Kanna?
Yes, ma'am.
Why? Because the sodium's quantity is very much lesser than the quantity of Na plus, which is absolutely wrong. And option 4 is also ruled out. Why? It shouldn't be same. Concentration of Na plus and concentration of sodium carbonate shouldn't be same. Could you please guess the answer? Definitely you can
B,
guess.
ma'am.
Sorry, Kanna?
B, ma'am.
That's it. Answer is B. So this we have approached this question only with the logic we know. We didn't even do any calculation here, right? But we end up with the answer, that too with the right answer, right? As I've told you already, there is another way of approaching this. First is calculate the concentration of sodium carbonate itself, because we have the weight and we can calculate and see molar mass is also given, and we have volume of the solution, so we can calculate the concentration of sodium carbonate, and that will be the concentration of carbonate ion, and 2 times will be the concentration of Na plus. So that is the normal way of doing it, but we have to be quite smarter, right? And time is very important. For calculating, at least we need 3-4 minutes, right? But if we know the logic behind this, and if we are lucky, as we told, second option was right. So if we are so lucky with this logic itself, we can find the right answer. Fine. Shall we move on to the next question, Kana?
Yes, ma'am.
Fine. Now here is the problem. The problem what I'm going to give you now is quite different, but this is also related to our molarity, but the data given is a little different here. Here the molarity of 98% sulfuric acid by weight is dash, and the density of sulfuric acid solution is given as 1.8 gram per ml. See, they're asking us to calculate the molarity of this sulfuric acid solution, but the data is quite different, right? So what is the formula we know for calculating the molarity? number of moles of solute divided by volume of the solution in liters, or weight of the solute divided by molecular weight of the solute into volume of the solution in liters, right? Here, what is the solute, Kanna? What is the solute here? What is the solute? They are talking about sulfuric acid solution. So what will be the solute, Kanna? Sulfuric acid, H2SO4, right? So M2 can be calculated, right? So could you please calculate the molecular weight of sulfuric acid? Atomic weight of sulfur is 32, oxygen is 16, hydrogen is 1. Please calculate the molecular mass of sulfuric acid. So it is 98 gram per mole. So this is the molar mass of sulfuric acid. Right, Sendamil Children's answer was right. Fine. So we have M2. We need the value of W2 and volume of the solution. First, we'll crack this W2. See, they are talking about 98% of sulfuric acid by weight. So what it means is, listen carefully, Kanna. I have a bottle full of sulfuric acid. Okay. I have a weighing machine on which I'm going to have a beaker, and I'm going to weigh 100 gram of sulfuric acid solution. Okay. Now in this beaker, I have 100 gram of sulfuric acid solution. From this 98% sulfuric acid, what we can understand is, in this 100 gram, 98 gram was the weight of sulfuric acid and 2 gram was the weight of water. So it is highly concentrated solution. Concentrated solution is nothing but solute's concentration will be extremely high. Okay. So here 98 gram was the weight of the sulfuric acid and 2 gram was the weight of water. So from this data, weight of solute can be derived, right? So what is the value of W2? It is the weight of sulfuric acid. So what is the weight of sulfuric acid, Kanna? It is 98 gram. You getting my point? So molecular weight was calculated, and from the data given, we derive the weight of sulfuric acid itself. Next job is, we have to find the volume of the solution, right, Kanna? It is also very easy. See here, to find the volume, density is given. What is the formula of density? What is the formula of density?
M by V, ma'am.
Yes. So density of the solution is given. So density of the solution is equal to mass of the solution divided by volume of the solution. Here our job is to find the volume of the solution. So V is to be calculated. So V is equal to mass of the solution divided by density of the solution. See, what was the mass of the solution? It is 100 gram. And density of the solution was given as 1.8 gram per ml. So gram will be cancelled. So what is the volume of the solution, Kanna? What is the volume of the solution? 100 divided by 1.8 is 100 divided by 1.8. Could you please calculate and let me know the value? Hundred by 1.8. Please come up with approximate value at least.
55, ma'am.
Okay. 55. Is it exact 55 or 55 point something, Kanna?
55.5.
Okay, 55.5, right. So volume of the solution is 55.5. I'm going to bring this per ml to the numerator, so it is milliliter. That's it. So we got the volume of the solution also. So weight of the solute is 98 gram divided by molar mass of solute is 98 gram per mole, and volume of the solution is 55.5, but we have it as in milliliter. I want it in liter, so I'm going to write the value of milli, which is 10 power minus 3 liter. That's it. Gram will get cancelled out. Per mole, I'm going to bring it to numerator, which is mole. Liter to numerator, which is per mole. So please simplify and come up with the value for molarity. That will be the answer. See, what I'm going to do is 98 will get cancelled, right? I'm going to bring this 10 power minus 3 to numerator, so it will become 10 power plus 3, which is 1000. So 1000 divided by 55.5. Options are broad here, so you can round off the value. It can be 1000 divided by 55 also. Any answer? Any approximate values?
$18, ma'am.
That's it. Very good, Kana. That's it. So answer is second option. Yes, Sendamil children's answer is also right. Superb. Now shall we move on to next concept? So we are done with this molarity part. Now we'll move on to next concentration expression, which is molality. Molality. Molality, and the way of representing it is small m. Okay, that is capital M and this is small m. And I'm going to represent it in terms of alphabets and I want you to read it. Okay, which means here this is number of moles of solute and this is the volume of the solution, right? So it is just the representation, but how I've read this, it is the number of moles of solute divided by volume of the solution, right? Now I'm going to write the representation and I want you guys to read it. N2 by W1. W1 is in terms of kilogram. Please read this expression, Kana.
Number of moles of solute by mass of the solvent, ma'am. Solution.
Very good, Kana. Mass of the solvent, yes. Here, N2 is number of moles of solute divided by W is weight, and weight of what? Weight of the solvent. And weight of the solvent has to be in kilogram. So what will be the unit then? For number of moles, it is mole. and kilogram I'm just bringing to numerator. So mole per kilogram is the unit of molarity. And I can expand this in terms of weight and molecular weight. So instead of N2, I can write it as W2 by M2 into weight of the solvent in kilogram. That's it, Kana. Shall we do one problem related to molality?
Yes, ma'am.
Here is the problem. You want to express the weight of solvent in kilogram. If it is in kilogram, no problem. But if it is in gram, please convert that into kilogram. Small m always represents molality. I'm going to read this question. Listen. Calculate the weight of sodium chloride required to prepare 5 molal 5 molal solution by dissolving 50 gram of water. If you guys want any clue, please let me know. I'll support you.
equal to m into m2 into w1.
Mm-hmm. So you don't know which formula to be used.
Yes, ma'am.
Fine. So now you guys are clear with this? Fine.
Yes, ma'am.
Next expression is normality. Next expression is normality. For normality, the representation is capital N and the formula is Ne2 by V in terms of liter. What is in the denominator? What is in the denominator?
Volume.
Volume of what?
Liquid. Liter.
Volume has to be expressed in liters, but what?
Volume of solution.
Volume of solution, right? Now here the difficult part is our numerator, which is different, right? Which is Ne. Ne is nothing but number of gram equivalents. It is similar to our number of moles. So number of gram equivalents. See, what is the formula of number of moles? This is number of moles of solute. The formula is weight by molecular weight, right? So similarly, number of gram equivalents of solute is nothing but weight of the solute divided by equivalent weight of solute. That's it. Instead of molecular weight, we have to write the equivalent weight. That's it, Kana. But we have to know the equivalent weight, right? That is also very easy. Now we are familiar with calculating the molecular weight of solute. Here is the formula to calculate the equivalent weight of solute. So E2 is nothing but equivalent weight of solute. And formula is molecular weight of the solute divided by n factor. So whenever we have a solute, it is possible for us to calculate the molecular weight of the solute, which is m2. Now we have to know the n factor of the solute to find the equivalent weight, right? See, this n factor is different for different chemical species. Now we'll understand that. Now for acids. For acid, we're going to find the equivalent weight. So what is the formula to calculate equivalent weight? Molecular weight divided by n factor. Right, Kana? So for acid, the n factor is nothing but basicity. For the chemical species acid, the n factor is basicity. Basicity is nothing but number of replaceable H plus ions. See, I'm going to calculate it for a couple of acids now. Let us take HCl. Could you please name this acid? Could you please name this acid? What acid is this?
Hydrochloride.
Hydrochloric acid. Hydrochloric acid. Now we're going to find the equivalent weight of HCl. First job is we have to find the molecular weight of HCl. What is the molecular weight of HCl, Kana? Hydrogen is 1 and chlorine is 35.5 gram per mole.
36.5.
Yes, so 36.5. And basicity is number of replaceable H plus ions. How many hydrogen this acid got? Only one, and that one hydrogen is the replaceable hydrogen ion. So here it is 1, so basicity is 1. So equivalent weight of HCl is 36.5. That's it. So I'm going to have second example, which is sulfuric acid. So what is the molar mass of sulfuric acid, Kana?
98, ma'am.
98. And now we have to find the basicity. See, all the hydrogens in the acids were not replaceable hydrogens. First of all, we have to find the replaceable hydrogens. So here, for that, we have to know the structure of all the acids. For sulfuric acid, the structure is S double bond O, single bond OH, single bond OH. Since this is the first chapter, you may find it difficult to write the structure, but after studying this chemical bonding chapter, you will be, it is possible for you guys to write the structure of any acid given. Okay. So now I have two hydrogens in sulfuric acid. If the hydrogens are attached with highly electronegative atom, or put it in a simpler way, if the hydrogens are directly attached with oxygen, then that is considered to be the replaceable hydrogens. So here, as far as sulfuric acid is concerned, we have two hydrogens and both the hydrogens are connected to oxygen. So what is the basicity of sulfuric acid? What is the basicity of sulfuric acid? It is 2. So what is the equivalent weight of sulfuric acid then? It is 49. That's it. Fine. Now one more acid kana, H3PO4. The name of this acid is orthophosphoric acid. So I'm going to find the equivalent weight. So it is possible for you guys to calculate the molecular weight, right? Atomic weight of phosphorus is 31 gram per mole. So what will be the molar mass? Sulfuric, for phosphorus, it is 31. So what
79.
Okay, Rakshan's answer is 71. 79, Rakshan?
Yes, ma'am, 79.
Okay. How about the rest of the students? Is it 71 kana? It is not 71 or 79. It is 98. Fine. Now we'll find the basicity. I'm going to write the structure of orthophosphoric acid. S double bond O, OH, OH, OH. So this is the structure kana. So what is the basicity of this acid? What is the basicity of this acid? Only 3 more minutes, please. So basicity is number of replaceable hydrogen ions here is 3, right? So that's it. So here molecular mass is 98 approximately. So if you simplify this, you'll get the equivalent weight of orthophosphoric acid, and Sendamal Children's answer is 33.33. Almost it is right, Kana. Right, your answer is right. So I have another acid. This is going to be your last acid now. After this, we'll wind up the session. Next class, we'll continue from here. This acid is called phosphorus acid. And the structure of this phosphorus acid is P double bond O. That is phosphorus is connected with oxygen through double bond. This is hydrogen. This is OH and this is OH. So this is the structure of phosphorus acid. Could you please tell me the basicity of this acid? Basicity of this acid. No. We got 3 hydrogen atoms here, but the hydrogens which are connected to oxygens were considered to be replaceable hydrogens. So here only 2 hydrogens were connected to oxygen. So replaceable hydrogens are only 2 and basicity is 2. Now it is easy for us to calculate the equivalent weight of phosphorus acid, right? So today we'll close the session here, and next class we'll continue from normality. Okay? Do you have any doubt, Kana? So today we have discussed what is solution, solubility, solute, solvent, concentration, molarity, molality, and numerical from limiting reagent. If you don't have any doubt, then we'll wind up the session.
Okay, madam. Thank you.
Thank you, sir. Thank you.